topic today is Advanced Assembly Modeling Part 1. And we actually planned even more content for this, but just last night, Chinnawit and myself decided to take out the other examples, maybe do that later on. So the example that we'll work on today is this one. It's a small assembly of two metal parts. The lower one is a steel plate. The upper one is an L-shaped, well, bracket or whatever you would want to call that part. It's bolted onto the lower one with one single screw, M10 thread, and it's an 8.8 screw, which refers to the strength of the screw. So that's, I could say, medium upper strength screw, pretty good quality. And this is important because it determines what the nominal clamping force is. So if you get a 6.8 or 5.5, you don't express the strength with the typical material properties that you would usually use, such as yield strength. But with a screw, you have this 8.8 code. And this is normally used for screws. 8.8, as I said, is pretty high up. You can look it up on the internet, what the nominal screw force is. That means the clamping force that results from the screw when you tighten it with a nominal torque. Right now, the weird thing is I didn't find an English language table that would give this information clearly. So down there, I've given you a link to a German website which has everything about screws. I use it quite a lot of times. So we have this assembly. There's an external force acting on it, and the lower part is somehow constrained. In this case, we've fully constrained the rear surface of the lower part. Now, why are we doing this today? What is the greater motivation? There's quite a lot of words in here, and I will not read through them. But you can read through them later on. So what we're actually doing in the MESD program is that we're studying simulation in the context of design. And this is very much the reason why we're looking at what we're doing today, which is basically strategies to simplify structural simulations or simulations on groups, on assemblies that have a structural function. Now, when you do that in the design context, you're not interested in running a perfect simulation that completely simulates reality, but usually you just want to make sure that your design is feasible structurally, which means you roughly know external forces, and you typically know what the critical area is, what I call the critical area in one or two parts, and you want to know at least the magnitude of stresses and deformations there, right? So the point is to find a modeling strategy which basically is as easy as possible and still giving you the results and the quality of results that you need. Now the bottom line is that any simulation is always based on a model, and any model is always a simplification of reality, and therefore there's always some error in your model and your simulation, always. The question is, how much error are you willing to allow? And the other question is this error relevant for what your question is? So for example, if you know what the critical area of your design is, you're interested in, let's say, level of stresses and deformations in that critical area. And the errors in your simulation don't affect that critical area at all, then it's not a problem, right? And basically, this is the approach that we're doing today, is that we're demonstrating two different strategies to simulate our little assembly here and the load case. Both are simplified. One is grotesquely oversimplified, and the other one is actually pretty good already. And at the end of this, we'll look at how the result in the critical areas, how they're different. And then we can evaluate what level of simplification is actually useful here. Now, why are we looking at assemblies? I said it already, in the design context, assemblies are pretty relevant. If you have some sort of method behind your acting, you will be designing in a top-down fashion, which means you'll basically have an assembly very early on. Typically, structural or linear elastic simulations with imported geometry, they often look at components, which is of course relevant, but if you're still in the design process, you're often, the more pressing question is, how does the assembly really behave? And this brings us to the biggest problem in simulation, is that it's really the interaction between multiple components that is most difficult to model, or at least it will cause way more computing time, and that increases the risk of the simulation just stopping unsuccessfully. And this can be really frustrating. Nowadays, it's not as bad as it used to be simply because of computing power. So if you have a bad model that cannot finish the simulation, at least you know it after a few minutes. But in the olden days, and even nowadays, depending on the size of your model, you might have your simulation running for many hours, and then at the end you'll find out, oh, it didn't work, I have to change something, but then nobody tells you what, right? So so basically the one big thing that I want to get across today is the very last point on this slide is first run the easiest possible simulation, which means the most simplified model that you can make of your assembly. Now, when we have different kinds of interactions with parts, this is basically where we can simplify the most. Basically, we can just eliminate all sorts of realistic interactions and just unify parts. This can be one approach. In assemblies, we typically have a lot of joints, standard joints, and they will cause complex stresses in the parts. Here, one part of the problem is that these joints and the stresses, or the area that are affected by the stresses, are typically very small in comparison to the overall assembly. And then if you think about meshing, that means you can't really simulate them. If you want to simulate, for example, what is going on in a thread, in a bolted connection, you would have to reduce the mesh size to simulate that thread. And that would mean a very high number of elements in your overall model, even in the areas possibly that are not very interesting to look at. So you either have to manually refine the mesh, or at least define where it should have a higher density, or that just creates more time, more effort. And typically you're not really interested in the stresses in a thread, for example, because everything is standardized. You're using a standardized screw, and as I said before, it is well defined how much it should be tightened, with what torque it should be tightened, and it's completely established that the materials, thread materials, are able to work with these stress levels. So you don't want to simulate that. So the question is, how do you actually simulate, for example, a bolted connection, or maybe a press fit? That is something we wanted to do today, but we cut it out for time reasons. We'll postpone that. So really, to run a simulation, and you are already aware of that, but many other people aren't, you have to have a good understanding of engineering basics, or even more than basics. Basically, some people say if you need a simulation to know what is going to happen, then you're not really qualified to run a simulation. So basically, you should be able to estimate what is going to happen in this load case, at least qualitatively, what sorts of deformations you have, and what sorts of interactions that will result in between the parts. And you should be able to estimate where the critical areas are. And ideally, you should even be able to roughly estimate by a hand calculation the level of stresses that might result. Okay, although that last one nowadays, well, it's always good for checking if your model is plausible, if the results are plausible. So these are the general pointers and introductions. So back to the load case that we're looking at again. I'm pretty proud of this little load case here. So we have this aluminium L-shaped thing bolted down with an M10 screw with a nominal screw force of 26.3 kilonewton, and the external force, which is acting on the vertical arm of this L-shaped aluminium bracket, 5 millimeters down from the top edge. And the question is, what would be a feasible or appropriate way to simulate that load case? What do you really want to know, or the question is, why would you want to simulate that? Not because of the screw, right? As I said, it's standardized. You can trust that the screw should be fine. Of course, unless this is that the external force overloads the screw, right? And this might well be the case here. You can see that this L-shaped thing might actually act like a lever. It might actually try to roll over the bottom corner of this L shape, and it will pull on the screw. So any external load acting as it is right now will increase the screw force, and it might, at some level, actually cause the failure of the screw. Right. Even worse, of course, in dynamic cases, the screw will loosen, but that is nothing that we are going to look at now. So basically, the main reason why you would want to run the simulation first is to make sure that the aluminium part will have stress levels that seem to be feasible, right? So the next question is, what do you really expect? Where would you guess the critical area is? What is the area with high stress levels that might need to be optimized by design? And this, even to non-engineers, should be pretty obvious. You have some sort of bending load case here. You will have the tensile stresses on the surface where the external force is acting on, and you will have a very high stress concentration in that corner. Tensile stresses, and then a big change of the loaded section. It's pretty obvious that we will have to expect the highest stress level here. So what I suggest is to start with a very, very simplified simulation of the assembly. And this basically is, of course, to completely ignore the screw. So you would import the CAD geometry without the screw. You don't want to simulate the screw. All the features are very small. That would just bring up the level of elements. Completely leave it out. And we'll go even further. We will not even take the screw force into account first, but we will just assume that the bolted connection will work, and that means there should be no movement between these two parts. So we will oversimplify these two parts as being unified or united, and in the most stiff and stupid way. And I always call that node to node. We're having guests, hang on. And I was kicked out and came back. Okay. So where was I? Okay. So instead of simulating the screw force, which is pushing these two parts together, we just join these parts by joining the two meshes of the parts node by node. And that would be more like gluing them together, but with a glue that is absolutely stiff. So it's almost like welding these two parts together, or it would relate to welding these two parts together, which of course in real life is really difficult with aluminium and steel. And we know, of course, this is not reality, right? But we consider this because we assume that we really only want to know what is really going on the inside corner of this L-shaped aluminium part. You should be aware of the errors that result from this simplified modeling. And in ANSYS, the model will look somewhat like that. So you import the geometry. Chinnawit will demonstrate all of that in great detail. You have to define the contact, or how these two parts interact. In this case, the most simple way by uniting them node on node, as I always call it. And then, of course, the loads and constraints. You can see that Chinnawit will define a surface. It is 10 millimeter high, and then we'll define that there's a load acting on that surface. So it's really a distributed force. It's more like a pressure, but it exactly represents what I was trying to say with the sketch at the beginning. What you cannot see in this screenshot is the fixed support that is going to be at the rear face of that brownish surface here. And that's it. Now the resulting error, of course, will be there will be no internal stresses resulting from the bolted connection here. What is most important here is that these two parts are really united, and we can expect they're trying to bend. Now you can even calculate that these two united parts will have a much higher stiffness against bending in this horizontal plane. That would be, if you would calculate that, the moment of inertia would not be only the sum of the two bending moments of inertia, but we even have a term, and that is really big according to the parallel axis theorem. Basically, this is a sandwich, right? And we know in real life that's not correct. In real life, we have we just pin down the one body at one position, and if it starts bending, it will probably lift off from the lower body and only support itself against the brown body on the edge, on the outer corner of this L. But if they're united as they are now, it will be the lower, all the two combined horizontal parts will be much stiffer, and probably the resulting stress in the inner corner of that L-shaped aluminium part will be even higher as a result of that. So again, Chinnawit will go through the whole simulation. I'm just quickly showing you the results, so you can watch him with a better overview. What happens here is pretty much what I laid out before. You will find the area of highest stresses on the inside of that corner on the L-shaped aluminium part, and the stress level here is, as you can see, around 200 megapascal. Chinnawit gave me a close-up here. What is interesting to note here, that basically all the nodes on this edge have different stress values, and they vary quite a bit. Maximum stress level is 220 megapascal, and a node around the middle of that part just has 170. And this is really resulting from the rather coarse mesh we have. On principle, this is a two-dimensional load case, right? So on principle, you should have the same stress level all along the length of this edge, but the simulation is pretty different. You have, I would say, variation, just roughly guessing, from mid-yellow, that would be 160 to 220, which is quite a lot of variation. So that is also an indicator that we shouldn't be trusting the numerical result as an exact result. Never ever, especially with this rather coarse mesh. And of course, the mesh is that coarse for two reasons. First, we want to save time. Second reason is we're using the free educational license here, and that is limited with regards to elements. Okay. So the next strategy would be, or the next level of complexity for modeling and simulation would be what I call strategy B, a more realistic interaction of the big parts. And that means the little parts are still fully ignored. So what we'll do now is we will still not simulate the screw itself, but what we will do is we will model the screw as the forces as the clamping force that it produces. And so that means we'll have a force pushing down at the contact surface between the screw head and the aluminum part. And of course, the magnitude of that force will be the 26.3 kilonewton. And in this case, if you looked at the sectional view that I've given you, you would see that the screw is not paired with a nut, but instead there is a thread in the lower steel part. So that means there will also be the same screw force pulling up on the steel part, and we'll also model that by by adding basically a force acting on the cylindrical surface of that hole in the lower part. We do that because we want to see also, we want to look at how the steel part actually bends or deforms under the acting external load. So the screw forces, they basically neutralize each other, right? But they simulate how the screw really fits the two parts. And this only makes sense if we allow a more complex interaction of these two parts. So this time we will not completely bond the two surfaces, the contact surfaces, but instead Chinnawit will choose an appropriate surface contact condition that actually allows for the surfaces to lift off from each other but not go into each other. And there's even the effect of friction between those. And this is necessary because if the two surfaces could move without friction, then the external force would just push the L away. So this is actually some pretty high level simulation that we'll do right here. And I would say that this is, for this specific example, is the highest level that you're really interested in as a designer. Unless, of course, you are a thread designer or a screw designer and you want to optimize the behavior of threads and screws, but we are not, okay? So the question again would be, what are the errors that we can expect here? They are pretty low. The only resulting errors are not from bad modeling or from oversimplified modeling, but really from, let's say, mesh quality and, of course, wrong assumption of the forces that are acting here. So this is going to be some pretty exciting result here. Okay, so the external force is acting as before. We have this red strip labeled A here, which is 10 millimeters wide. So that relates to the force acting 5 millimeters under this external edge. And then we have the two screw forces called B and C, same magnitude, one acting up, one acting down. Fixed support on the back. And what you can't see from that screenshot, and this is maybe the most interesting bit, is how this contact between the two parts is defined. Just as a quick preview, the stress levels that you achieve here are in the same order of magnitude. They seem to be slightly larger here. And this is contradicting what I said initially, because normally I would expect them to be larger in the oversimplified model, again, because the jump in stiffness, in bending stiffness between the vertical arm of the L and the base is much bigger. And I still kind of insist that might be the case. Here, the stress level that is shown here in the nodes, in this knee, as you could call it, are a little bit higher. It says 207 here. On the same node in the other model, I believe it was 180, but I have that comparison in the next slide. Now, the highest stress level in this model is where the head of the bolt is pushing down the aluminum part, but you can just easily ignore that. Okay, just ignore this stress level. Typically, when I would show simulation results to a client, for example, it's often a good psychological idea not to show these nodes anyway. They just basically, they distract, and it's meaningless stress level at this position. What is really meaningful is what is happening on this edge of the aluminum part. So if you compare them again, what I just said, in model B you have a higher stress level, but just slightly higher. You could even say, well, on model A the maximum stress nominally is around 220 megapascal, and on the lower edge, it's possibly around 220, so it's almost the same. So I believe it's actually really, if you would take all of the nodes, or if you run both simulations with a really fine mesh, you would probably get the same stress level. And this is the story that I want to tell here, is that the interesting result is, how is your own design aluminium part performing? This question can often be answered in an appropriate and satisfying way by a very, very simplified model, as we do in case A. And this is maybe the one story that I want to tell here, is we don't simulate for simulation's sake, just to simulate everything we can do. We should be able to do it sometimes just to check if our assumptions are really correct. But often the strategy of really uniting multiple parts in an assembly at their contact surfaces just makes sense if they are assembled with a fixed connection, such a bolted connection, for example. Okay.
Okay. Hello everyone again. My name is Chinnawit. I am a researcher assistant of the MESD program at TGGS. Today I am going to talk about how to model an assembly problem by using ANSYS. Okay, last time we used the model analysis type of analysis type of model analysis. Okay, so today we going to talk about the static structural. Okay, let's start. You click the static structural and drag to the schematic area. For the first problem, you have to use the two types of material, one for structural steel and aluminum alloy. So first step, you have to click the engineering data and click edit. So the top table show you ANSYS already select structural steel. If you want to add more material, you have to click the engineering data sources and click general material and add the aluminum alloy to your library. Okay. And then now the aluminum alloy already defined in the ANSYS. Close the window. You will see the aluminum alloy and structural steel in the engineering data. So close the window and click geometry, right click and import geometry. Select and open. You can now click geometry and edit geometry in Design Modeler. When you open, you have to right click import and click generate. So now you can see your model in the window. Okay. Now you have to part, L block, and this. First, you have to position this surface by click this surface and sketch. I just try another approach. Okay, so now we can define the distance of these 2 points from the top. Now the unit is in mid. You can change the unit in millimeter by click this unit and click millimeter, and then change the value to 10 millimeter. Okay. After drawing a line on the surface, go to Tool and click Face Split. The target face is this face. And then apply for the two geometry. Click this line, activate the selection edge and click line, apply. And go to face split again, right click and generate. The green tick appear. That means this surface already positioned in two area, top and bottom. Okay. So close the design modeler and go to model, right click and edit. Okay, now your model already open in the model editor. Click geometry again and you see our block and base. Now you have to assign the material property as an aluminum alloy to the L block by click this option. You click aluminum alloy. And for the base is already assigned as a structural steel. Don't need to change it. You open the contact. By default, there is one contact between two parts. You can rotate the model to see where is the surface contact. The surface of the L block and the surface of the base. When you import the assembly geometry in ANSYS, the program already assigned the type of contact as a bond surface. That means two parts are perfectly attached together. Okay, you don't need to change anything in the option. Leave it by default and go to the mesh process. In mesh process, I suggest you begin from the 5mm, right click and generate mesh. So you can see the number of node and element by click statistics. I would like to refine the mesh on this area. So you can refine it by right click mesh, insert, and choose refinement and select to surface. Apply. And then right click on mesh and click update. Okay. Each better because we refine the mesh on this surface, and you can see the increase of the node and the element. Okay, next step. We will define the force acting on the top of the L block. Right click the structural steel, insert, and choose force. Okay, click this area and apply. And input the magnitude of force. I suggest you define by the component. We want to push this area in the minus x direction. The force is 10 kilonewton. So next step, we define the boundary condition, the real surface of the base. Click structural, again insert, and choose fixed support. Click this surface and then apply. Now your model is already define the force and the boundary condition. Right click solution and choose solve. Okay. You can insert the value that you want to see after the simulation by right-click the solution, insert, and then choose stress and volumetric stress. Right-click again, and then evaluate our results. Now, your results appear, and you can see the maximum and the minimum by click this label, or you can click probe and choose where you want to see a stress on the body. Okay. And you also see the animation. By click the animation tool, and you can see the behavior of the model like this.
Okay, now this, well, I would like to comment again, just to connect to what I said before. If just what you showed us just 1 second before is the side view, you can see how the lower part of the aluminium part and the steel part are really acting as one stiff body. This is what I meant with that. Basically, we are creating a sandwich that is not really a sandwich, right? So we're not only adding the two bending stiffnesses, but through the stiff bond, it's basically becoming, you could say, it's basically becoming 8 times stiffer than before, right? Just assuming for a second this would be the same material because of the basic formula of the bending moment of inertia, right? That has the height of the profile to the power of 3. So this is now acting as if it was 8 times stiffer than each of the two parts. And if you just look at the deformation of the L, or basically they both bend up together, right? So there's, on the left side you see a short, pretty soft bending beam, then suddenly it becomes 8 times stiffer than it was before. And the same to the vertical part. It's pretty flexible, but then it meets the bit that is completely stiff. So that should, in my expectation, should increase that big jump in stiffness should increase the local stresses we have on the inside of this aluminium part.
For the second modeling, we replace a screw by adding a screw force on the top, on this surface of the L block. So I will close, minimize this window, and then I can click this option to select duplicate, right? Duplicate. We don't need to start from 0. Okay, we just edit the surface in the geometry and select in the design modeler. Because we have to create another split surface at the top, of the hole, you click this surface and sketch and to draw a circle on this surface. Click dimension and define the diameter of the circle around 16. This area representing the washer compressed on the top surface. Again, click tool, face split, click this surface as a target face, apply, and the geometry you change the filter, select edge, and click a circle, apply, and then click split surface again, generate. Okay, so now you already create the split surface at the top of the hole, and close, design modeler, right click model, edit. Okay, your model already open in the modeler. You make sure that the L block already assigned as an aluminum alloy and the base already assigned as a structural steel. For the contact, we will remove the bond contact and replace with a frictional contact. You can click this option, the definition of the contact type, change the bond to the frictional. The friction coefficient is between aluminum and structural steel is 0.6. Okay, and mesh again. Now, force is the same. The boundary condition of the fixed support you don't need to change. And now you add the force acting on this surface. Just right click and insert force. Select this area and click apply. The magnitude of the force, change the option to component. The force acting normal the surface in the minus y direction. The force of the screw is 26.3 kilonewton. Make sure that it's a correct direction, the minus sign. Okay. And the force at the thread, you can select insert force again and click the cylindrical surface. Defined by component in positive y direction. Okay. Right click solution and solve. So now you can see the results of the simulation. You can see the stress appear on the top of the hole, and the area of the thread. You can see the animation.
Yes, show us the side view, please.
This view.
Yes. Now let's see what happens when the force is full on. Yeah, you can already guess that the two surfaces are actually separating from each other. That it seems to be a small gap. Is it possible to increase the scale of the deformation?
deformation.
Okay, you see it already. What is this, the scale of the deformation? Is that it's not natural scale, right?
Yes, not natural.
It's probably like 100 times actual scale, right? Okay, but that's clear enough. Pretty beautiful. You can see how the L is leaning onto the steel part with the rear edge and lifting up in the middle, and that actually means that the probably that the screw would be stretched. Obviously, now there's the external force. It will result in an extra force acting on the screw, stretching the screw a bit more. But we don't know about this. We don't have the screw in the model. We have constant forces acting on the upper and lower part. Now, if you stretch the screw, of course, it will react with a higher reaction force. And this is modeled wrong here, basically, because our screw force is modeled as a constant force. In real life, any try to stretch that screw would result in a higher reaction force. So I believe the gap that we see here in this simulation, or if we would measure, if we would determine the size of the opening of that gap, it would be larger in this simulation than in real life, because in real life, the screw force would increase. And therefore, probably here it's constant, so probably the resistance against the opening of this gap is a bit lower here. But this doesn't really matter because we were never really interested in looking at the screw anyhow. Also, we don't worry too much about a separation of the two parts or a failure of the connection. What we're really looking at is the stress level in that corner, on that edge. So so can you zoom us in on the results, on the stress results of that corner? I already checked it out. The nodes are just getting orange, so to speak. So the stress level around the nodes on the edge is around 210, maybe 220 megapascal again, as we saw in the preview. Just judging by the color, you see some of the middle nodes are just getting orange, so to speak. And if you look at the scale, that means they're around 210, 215 megapascal. While the others are still yellow, so under that value. So again, the we could now, as you just did, you just put a what do you call that? Just pick up the stress value at the node. You could look at all of these, and I guess maybe the average value would be pretty close to the other model that we had. And again, I'm wondering if it's really true, what seems to be indicated here, that the stress level is slightly higher than the oversimplified model, because it could be the other way around. It could be slightly lower here because the added flexibility of the part actually could also result in a somewhat lower stress level. But this is not 100% clear which effect is stronger here, the this what we call notch effect, or the flexibility of the part, which allows higher deformations. Okay, I think this is very satisfying. I have to say, I was really happy that the model came out, the simulation came out as well as it did. What I really like about this is that we have pretty high stress levels in both parts simultaneously. So you can see that the steel part, can you zoom so we can see the steel part a bit better too? You see von Mises stress. Sorry, I mean zoom out.
Oh,
zoom
sorry.
out so we can see the steel part. So obviously it's von Mises stress. So it's if we would look at the maximum principal stress, it would be tensile stress on the bottom, compressive on the top. Here with von Mises, it's always a positive value, similar value going into the green region. Hello, sweetheart. So around 120 to 150 megapascal, pretty high stress level for the steel part, probably depending on the steel under yield. and the bending part on the aluminium is well, it varies. Near the corner, it's getting into the same region. So we have similar stress level. If you have high strength aluminium, that would give you maybe a yield strength of around 200 megapascal. Regular steel has a similar yield stress. So I would say if this was my structural design for something, I would be pleased with the general design. I would not be pleased with the stress concentration in the corner. So I would want to change the detailed design of that aluminium bracket, the aluminium part, so we don't have a high stress concentration in the corner. So now I'll be quiet for a moment. I'll hand it back to you if there's anything else you want to comment on that results, on these results.
Okay, if anyone want to see the displacements, you can click the solution, insert the deformation. So you can see the results in each direction. And you can choose the deformation scale because by default, it selects 10 times. If you want to see the true scale, you can choose this. You can see the you can select the result that you want to see and then click and evaluate to see that result. I think it's that's my comment for the results, for the see the how to see the result after the simulation.
Again, what I mentioned while we were discussing the simulation results, if I was a designer and this was my work, I would say I'm pretty happy with, let's say, the stress level on both parts, because it means I'm utilizing the material. So I'm getting close to the yield stress, which means I've not wasted any weight, any material. Only exception being that edge, that corner on the inside of the aluminium part. And this is your assignment: improve the design of the aluminium part to remove the stress concentration in the knee, or that inner corner. Or in other words, try to reduce the stress level there. And I'm not telling you how to do that. And I'm not telling you how many % you should reduce it. Just try to get it down. And this is your assignment, because it makes you think about, which is basically a standard in engineering, how to reduce the stress level on that corner. So try it out. And of course, use the similar modeling approach. As I said, on principle, it should be enough to use the very simplified, simple model, because the results in that critical area are very similar to both approaches. Of course, if you enjoy, you should try both approaches, just so you practice the modeling of the more complex surface interaction between the two parts. But your assignment is change the design of the L-shaped aluminium part, it must not become bigger, right? So just making a big massive part doesn't help. You must keep the same original envelope, so the basic L shape must remain. And you will also use the same screw, the same steel part. I've given you the my original Creo files. They're uploaded on the shared drive, as you would expect them. So that's basic undergraduate mechanical engineering knowledge. I think I'm not giving away too much if I'm saying that you can actually reduce stress by removing materials sometimes, right? And then I hope when you simulate that, you don't run into problems that your ANSYS educational version has a limitation to element numbers, right? So that's going to be a bit difficult, I'm saying, and I'm not expecting huge improvements and fantastic results, but this is your assignment. Try this out a bit. Bye bye.